Imagine this. You look up at the sky, but instead of visible light, your eyes could see X-rays. Among the stars and the galaxies, you notice a peculiar phenomenon: tiny dots flickering in the night. These flickers are caused by neutron stars, some of the most extreme objects in the universe. It's as if their twinkle is trying to tell us a story. But what? That's what I want to find out. My name is Inga Saathoff. I come from a small town in northwestern Germany. I was first introduced to astronomy when I went on a high school exchange program in the United States. I was immediately fascinated by how much we can learn about our universe just by looking at light. From then on, I knew that I wanted to be an astrophysicist. After completing my PhD in Germany, I moved to Stockholm to work as a researcher at the Oscar Klein Center in the Department of Astrophysics at KTH, the Royal Institute of Technology. So what are X-rays? Light is characterized by its wavelength and energy. The shortest wavelengths that humans can see are blue and violet. At even shorter wavelength, we first encounter ultraviolet light, the light that can give us a tan in the summer. As the wavelengths get shorter and shorter, the energy of the light increases. X-rays have a wavelength that is smaller than a few nanometers, 10,000 times smaller than what we can see with our eyes. Because X-rays contain so much energy, they're created in some of the most extreme phenomena in the universe. But to see them, we have to go beyond our protective atmosphere and study X-rays from space. In 1970, NASA launched the first space telescope to scan the sky for X-ray sources, the Uhuru satellite. During its mission, Uhuru detected several periodic X-ray pulses coming from different directions. Looking closely at the pulses, astronomers found that the X-rays were produced by remarkably small objects, neutron stars just 20 kilometers across. Such compact objects are left behind when massive stars die and explode in a supernova. A handful of neutron star matter weighs as much as a small mountain. These extreme objects have extraordinarily strong magnetic fields and can spin several hundred times per second. But where do the X-rays come from? Just as many humans form couples, so do stars. Many neutron stars orbit a normal star and can suck in matter from its companion. This matter is funneled along the strong magnetic field, crashes into the two magnetic poles of the neutron star, and releases copious amounts of energetic X-rays. As the neutron star rotates, we see these X-rays as pulses of light, like a lighthouse, coming and going. This is called an X-ray pulsar, and it is the source of the flickering we see in the sky. So this X-ray flickering tells us a story about the accretion processes and magnetic structure of neutron stars. If we learn how to carefully listen to the details of this story, we can therefore understand how matter behaves in one of the most extreme environments in the universe. But there's a problem. All the light from the neutron star is mixed together. We don't know which pole is emitting the X-rays. Because of the strong gravity around the neutron star, it can even happen that the light is bent around the star, and we see both poles at the same time. Therefore, I try to disentangle the information in the X-ray light, or to put it another way, I try to train us to listen better to what the neutron stars are telling us. Think of a cocktail party. Suppose you're talking to someone, but there's lots of other conversations going on around you. Despite all the noise, our brains are incredibly good at picking out the conversation we want to hear. Much like the cocktail party, I want to disentangle the voices of light coming from the neutron star, to see which part is coming from which pole. It's like tuning into different conversations at the party. But while our brains are good at this, our computers still struggle. So I have developed a method called phase correlated variability analysis, or PCVA for short, to listen to the story of neutron stars. PCVA works by looking at the temporal changes in the X-ray signals to see which light is coming from the different parts of the neutron star. To test this, I created simulated data, mixed the signals, and then used PCVA to separate them. And it worked! We can tell which X-rays are coming from each magnetic pole and analyze their specific properties. So what did we learn about the neutron star story when I used this technique? One of the most famous neutron stars is called Centaurus X3. It was the first X-ray pulsar discovered by the Uro satellite. When we listen to its flicker more closely, we realize that the light beam looks different when it is coming towards us than when it is going away from us. In other words, its pattern is not symmetrical. This was surprising because we often assume that there is such a symmetry. Maybe the magnetic structure near the surface of the star is much more complex than we previously thought. This could happen if the magnetic field lines aren't perpendicular to the surface of the neutron star at the poles. This result will help us understand more details about the accretion processes and the magnetic fields of neutron stars. It is another piece in the puzzle of understanding X-ray pulsars and the mysteries of the universe. And together with my colleagues at KTH, I will continue to refine this method and use it to teach the next generation of researchers.